There is a number that food scientists quietly track, and most people who eat packaged food every day have never heard of it. It is called migration. It refers to how much of the material a container is made from ends up inside the food the container holds. For decades, the assumption was that packaging and food are separate things. The can holds the soup. The plastic holds the cheese. The wrapper is not an ingredient. That assumption has been expensive to hold. To understand why, you need to go back to the moment when industrial food packaging became the infrastructure of modern eating. By the middle of the 20th century, food manufacturers needed containers that were cheap, lightweight, scalable, and inert. Inert was the key word. The ideal material would sit next to food and do nothing, a passive shell. Glass came close, but it was heavy and breakable. Metal was better, but metal corrodes when it contacts acidic food, and the inside of a can holding tomatoes is a very acidic place. So engineers lined the inside of metal cans with a polymer coating. The coating that won because it was chemically stable, easy to apply, and produced a clean-looking seal was an epoxy resin built from a compound called Bisphenol A, which most people now know as BPA. The logic was sound. Epoxy resins were already used in industrial settings. They were considered chemically unreactive, and the early safety testing at the time showed no obvious harm. A person looking at the evidence available in the early 1960s would have been entirely reasonable to sign off on this. The first crack appeared not in a can study, but in a laboratory accident that nobody publicized well. Researchers storing liquid in polycarbonate lab flasks made with BPA, noticed that the compound was leaching into the contents even at room temperature. Polycarbonate is a different material from epoxy resin, but both are synthesized using BPA as a building block. The shared architecture mattered. If polycarbonate released BPA into a flask of water, the question became unavoidable. Was the epoxy lining in a food can doing the same thing? The answer, when people looked carefully, was yes. Studies measuring BPA concentrations in canned food showed levels that were low by industrial chemistry standards, but were not zero. The first working model people reached for was a simple threshold model. Below a certain dose, the compound passes through the body without consequence. Above that dose, it causes harm. This is how we think about most toxins, and for most toxins, it works. The regulatory limits set under this model, somewhere around 50 micrograms per kilogram of body weight per day, were comfortable margins above what any normal diet would deliver. Then the threshold model ran into a problem it could not survive. BPA is not metabolically inert. Its molecular shape is close enough to estradiol, the primary estrogen in the human body, that it can bind to estrogen receptors. This makes it what researchers call an endocrine disruptor, and endocrine disruptors do not follow the ordinary rules of dose response. Hormones work at concentrations in the parts per trillion. The signaling systems they govern are calibrated for vanishingly small quantities, and an outside molecule that mimics the signal can cause measurable effects at doses far below what the threshold model considered dangerous. This is the part that rearranges the intuition. The standard logic says more exposure equals more harm. The biology of hormone signaling says that sometimes a smaller dose of an estrogen-mimicking compound causes a larger response than a bigger dose because receptor systems saturate and compensate in nonlinear ways. Studies in rodents exposed to low-dose BPA showed altered mammary gland development, earlier onset of puberty, and changes in prostate cell behavior. The doses producing these effects were sometimes below the regulatory safety limit. The research community did not handle this cleanly. There was a real conflict in the data. Government-funded studies using one strain of rat tended to find no effect at low doses. Academic laboratory studies using different strains and different endpoints tended to find effects. Critics argued the academic studies lacked rigor. Academic researchers pointed out that the industry-standard rat strain used in regulatory testing had an unusually high background level of estrogen sensitivity that might obscure a subtle signal. Neither side was obviously fabricating results. They were, in part, measuring different things with different tools. What broke the stalemate, at least partially, was epidemiology. Researchers began measuring BPA in human urine because the body clears it relatively quickly, and correlating those measurements with health outcomes across large populations. The findings were not clean, but they pointed in a direction. Higher urinary BPA concentrations were associated with increased rates of cardiovascular disease markers, altered thyroid hormone levels, and in several cohort studies, a modest but statistically detectable association with breast and prostate cancer risk. Association is not mechanism, and honest researchers said so. But the mechanistic picture was filling in separately. BPA and its metabolites had been shown to promote the proliferation of estrogen receptor-positive breast cancer cells in culture. They had been shown to interfere with the BRCA1 protein pathway in ways that could reduce the cell's ability to repair DNA damage. A compound that makes cancer cells grow faster and makes it harder for the body to fix genetic errors is, by any straightforward reading, worth taking seriously. The packaging industry's response was to replace BPA in many products with structurally similar compounds, primarily Bisphenol S and Bisphenol F, which could be marketed under the label BPA-free. The problem is that BPS and BPF are close chemical cousins. Early safety assumptions about them were almost exactly as optimistic as the early assumptions about BPA had been, and early research on them is beginning to show early echoes of the same pattern. Here is what the search actually teaches, separate from the chemistry. Hard problems in public health almost always get solved slowly, wrongly, and by people who maintained careful records across decades. The error in the BPA story was not that engineers chose a bad material on bad evidence. The error was that the threshold model was borrowed from classical toxicology without asking whether it applied to compounds that mimicked biological signals rather than simply poisoning enzymes. The model was right for the wrong class of problem. Recognizing that took 30 years and a pile of contradictory studies. So here is the finished idea, stated plainly. Certain synthetic compounds used in food packaging, particularly BPA and its structural replacements, can migrate from the container into the food. Once ingested, these compounds can bind to hormone receptors in the body. Because hormone systems are exquisitely sensitive to small concentrations, the doses that arrive through normal diet may be biologically active even when they fall well within limits calculated by models that assumed dose response was linear. The cancer-related concern centers specifically on estrogen-sensitive tissues and on disruption of DNA repair pathways. What this model cannot fully explain is individual variation. Two people with identical dietary exposure show very different urinary BPA levels and very different receptor sensitivity profiles. The genetic and microbiome factors governing that variation are still being mapped. The edge of current understanding sits exactly there on why the same exposure hits some people much harder than others. If you want to follow this further, the primary literature includes research from the National Institute of Environmental Health Sciences, peer-reviewed work by Frederick vom Saal on low-dose effects, and the European Food Safety Authority's reassessment reports, all of which are linked in the description.